Today, we're talking about Spring, which is a compression tool for FASTQ files, containing, as it says on the GitHub page, up to 4.29 billion reads. Why is this so important? Well, FASTQ files, to represent NGSS data, can be really large. For an RNA-seq experiment with 70 million reads that are each 150 base pairs long, it's a pretty common experiment. That file can be anywhere between 36 and 40 gigabytes large. And that's just for one sample. In order to have a biological experiment, you need multiple samples representing replicates and conditions and treatments, etc. Depending on how complicated it ultimately gets, you could have a lot of samples. And this could, in time, add up to be terabytes or petabytes of data. And so we need a way in order to transport that data between different groups, machines, etc. And you also need a way to store it long term once the primary analysis has been completed. And so FASTQ compression aims to do that by storing the data in a format that is a lot more compact. This is so important, in fact, that the European Nucleotide Archive includes, as its FASTQ FTP, the downloading method, it includes it in already a compressed format. This one is so common that most RNA-seq analysis tools or NGSS analysis tools are able to work with it automatically and compress and decompress the files associated with it. Of course, though, new compression methods are always being developed in order to improve this process, make it even more compact, and Spring is one of those methods. They took a look, as in Table 1 here, at these different data sets or applications, and then the original sizes, and then seeing what the improvement was over previous methods. And on average, the improvement was around 1.3 times. As you can see, there are two different modes. Lossless mode means that no data is lost in the compression and decompression process. All of the original data that was in the file, which includes mainly the actual reads themselves, and the quality scores associated with those reads. All of that is maintained throughout the process. In lossy mode, the read data is maintained for Spring, but the quality score data will not be as easily, or some of that quality score data will be lost in the process of compression and decompression. And so they recommend against using lossy mode if you're using data from newer Illumina sequencing machines, specifically NovaSeq and newer. Older data, you may get basically lower compressed sizes for lossy mode. But if this is the only way that you're going to be storing the data with a Spring file, you probably just want to use lossless mode to be safe. Spring is available via Bioconda. However, it is only available for Linux machines through Bioconda. And here is a test case for it in a Google Collaboratory notebook. This typically has around 12 gigabytes of RAM, 100 gigabytes of storage, and operates with a Linux OS. I've showed this code before, but this is how you install Bioconda in one of these Google Collaboratory notebooks, and that allows for programs like Spring or any program available via Bioconda to be installed into the notebook and utilized. So this is the process by which that occurs. And then these are the specific pieces of code that allow for the compression and decompression process. So the -C represents that we're compressing a file, as opposed to -D, which is decompression. Your input file and your output file, notice that the output file has a .spring associated with it. And then this T appendix, which represents the number of threads on the machine. In this case, I kind of guessed because I don't know the exact specifications for the machine that Google is allocating at this exact moment. And there's a whole bunch of information thereafter printed as the process goes through, underscoring different aspects and different sort of properties for your file, and of course how long everything is taken. It took approximately 334 seconds to complete this entire process in my case, and it took an originally 3.2 gigabyte FASTQ file and turned it into a approximately 307 megabyte Spring file. It also took 113 seconds in order to decompress the Spring file back into a FASTQ file. In the paper, the authors note that as you increase the size of the FASTQ file, the amount of memory necessary to run the program increases, which makes some sense given that they're trying to sort of structure it in a more complicated fashion as the size goes up. So it's important to keep in mind that if you're working with FASTQ files that are too large, you may need more high-powered machinery than what is available typically in a Google Collaboratory notebook or on a personal computer. The last note is that I'll mention is that the GitHub page contains a lot of information about all of the different options available. There are numerous ones in addition to how to work with paired end reads with the program versus the single end example that I just showed. So if you're going to be working with Spring, I would highly recommend reading through this page and making sure that none of the other options would be helpful in your situation, and making sure that you are utilizing the right template code from here. Thank you very much for listening.